Why do we bother putting telescopes on the top of mountains? The logistics of getting them up there is a nightmare. They're often very far away from the universities where the astronomers and astrophysicists actually work, and surely raising a telescope by a couple of kilometres doesn't make much difference to the viewing quality, does it? This question was posed to me a couple of years ago by one of our GCSE astronomy students and gives us the inspiration for this, our second video in the Random Astronomy Questions series. The atmosphere of the Earth is really quite small compared to the planet itself. The average radius of the Earth is around 6,400 kilometres. It bulges slightly around the middle for reasons that aren't important for today's video. Compare that to the atmosphere though, which is only 100 kilometres thick until we get to the edge of space.
This means that if we drew the Earth to scale with a radius of 64 centimetres, then the atmosphere would only be a 1 centimetre thick layer around the surface of our planet. How much does the variation of the Earth's surface compare to this though? Well, at its lowest, the Mariana Trench in the Pacific Ocean drops down to 11 kilometres below sea level. That is just 1.1 millimetres on our scale. In the other direction, Mount Everest, the tallest mountain on Earth, reaches 8.8 kilometres above sea level. On our diagram though, that's just 0.88 millimetres.
To give you an idea of just how small this is, you would need a micrometer screw gauge to accurately measure the height of the tallest mountain on Earth using this scale. When we observe stars and other objects in space from Earth, the light has to pass through the atmosphere to reach us as an observer. In the process, a lot of light gets absorbed and some light is scattered. We looked at the scattering process during our video on solar and lunar eclipses, with shorter wavelengths of light, like blue, being scattered more than other colours. The further the light travels, the more it is absorbed and the more it is scattered. This is why if you look at distant hills, they will seem less bright and bluer instead of their true colours. This also impacts on the quality of light reaching observers on Earth. The more atmosphere that the light travels through, the more scattered it becomes. This is why red stars might not appear as clearly red for an observer on Earth as they would from satellite imagery.
This is why when we observe objects, we try to do so when they are highest in the sky. If it is close to the horizon, then the light has to travel through more of our atmosphere to reach the observer, leading to poorer quality observations. There are also issues with sky glow, but I'm sure we will deal with these in a future video.
As such, it makes sense to gain altitude, as this further reduces the distance through the atmosphere that the light has to travel to get to the telescope. On the face of it, it may seem that moving a telescope a couple of kilometres up wouldn't make much difference, because the vast majority of Earth's atmosphere seems to be above there. But that is based on the assumption that the air has the same density at all altitudes.
In actual fact, the density decreases with altitude, as does atmospheric pressure. This is why it becomes harder to breathe at higher altitudes. As a quick aside here, if the atmosphere's density stayed at the same value as it is at ground level, then the atmosphere of the Earth would only be 8.4 kilometres thick. This would be a problem, as Mount Everest is 0.4 of a kilometre taller than that, so anyone who summited Everest would be an astronaut.
Thankfully for astronomers though, the atmosphere does get less dense as our altitude increases. This means that the mass of atmosphere above you does not change linearly with height above sea level. In fact, by the time you get to 5.6 kilometres, you've already passed through 50% of the Earth's atmosphere, with 75 to 80% of the atmosphere within the troposphere, which is the lowest layer of the Earth's atmosphere. So while it might seem like a small difference in terms of the total size of the atmosphere, increasing your altitude by just a couple of kilometers can reduce the amount of atmospheric disturbances versus observing at sea level by a significant amount.
The actual process of putting telescopes on the top of a mountain can be a complicated one, though. To start, the tops of mountains are rarely level, so will often need flattening, either by explosive or other means. As well as this, the parts for a telescope are often constructed in labs hundreds, if not thousands, of miles from the mountain. Transporting these parts safely requires roads to be built on the mountainside and trucks to transport lenses, sensors, and other delicate parts without damaging them. After all this, they can begin constructing the telescopes and start the actual observations.
This whole process is understandably complicated and can be expensive, so with your run-of-the-mill telescopes, it's unlikely that you're going to have the funding to put them on the top of a mountain. On the face of it, putting telescopes on a satellite and launching them into space on a rocket seems like a great solution. However, besides the expenses of a rocket launch, which often start in the millions of pounds range, there are several risks and challenges that telescopes mounted on satellites will face. Here are three. First of these is the danger of damaging the telescope during launch. As a spacecraft takes off, it will undergo high forces and vibrations, which can cause significant damage to anything other than the most robust satellites. Secondly, the size of the telescope is limited by the carrying capabilities on the spacecraft it is on. This often leads to smaller sized instruments being launched into space than we would build on Earth. Third, and finally, if something goes wrong with a ground-based telescope, you can easily send engineers to go and fix it, whereas a telescope in orbit is a much harder destination for repairs.
In fact, the only satellite that I can think of that has had manned missions to it for repairs is the Hubble Space Telescope, which has had 2 maintenance missions in its 30-year operational history. And as a fun little aside here, one of my professors at university, Jeff Hoffman, was one of the astronauts on one of those missions.
That concludes our second video from our random astronomy question series. If you've got anything you'd like to know, please do let us know down in the comments and consider giving us a like and a subscribe while you are there. Next week, we'll be looking at what happens if you go skydiving on a gas giant. So until next time, please continue to watch this space.